Welcome to myprojectbazaar.com. Now we are going to discuss about the product for an efficient single and double adjacent error correcting parallel decoder for the 24,12 extended Goli code. Now we are going to see the abstract for the product. Memories that operate in harsh environments like for example space suffer a significant number of errors. The error correction code are routinely used to ensure that those errors do not cause data corruption. However, ECCs introduce overheads both in terms of memory bits and decoding time that limit speed. In particular, this is an issue for applications that require strong error correction capabilities. A number of recent works have proposed advanced ECCs such as orthogonal Latin squares for different set codes that can be decoded with relatively low delay. The price paid for the low decoding time is that in most cases the codes are not optimal in terms of memory overhead and require more parity check bits. On the other hand, codes like the 24,12 Goli code that minimize the number of parity check bits have a more complex decoding. A compromise solution has been recently explored for both of three Hawkline codes. The idea is to implement a forced parallel decoder to correct the most common error patterns, single and double adjacent, and use a slower serial decoder for the rest of the patterns. In this brief, it is shown that the same scheme can be efficiently implemented for the 24,12 Goli code. In this case, the properties of the Goli code can be exploited to implement a parallel decoder that corrects single and double adjacent errors that is faster and similar than a single error correction decoder. The evaluation results using a 65 nanometer library show significant reductions in area, power, and delay compared with the traditional decoder that can correct single and double adjacent errors. In addition, the proposed decoder is also able to correct some triple adjacent errors, thus covering the most common error patterns. ECCs add parity check bits to each memory word to detect and correct errors. This requires an encoder to compute those bits when writing to the memory and a decoder to detect and correct errors when reading the memory. These elements increase the memory area and the power consumption and can also reduce the access speed. These overheads increase with the error correction capability of the ECC. Traditionally, codes that can correct a single bit error per word have been used. In particular, single error correction, double error reduction codes that can also detect double errors are commonly used. Microcontrollers affect cells that are close together. A number of codes that can correct double adjacent and triple adjacent errors have been recently proposed. These codes in many cases do not require additional parity check bits and in the rest require only one or two additional bits. The decoding complexity increases but in many cases can still be implemented with limited impact on the memory speed. These codes are useful for applications in which the error rate is low. However, when the error rate is large, codes that can correct errors on multiple independent bits are needed. Now we are going to see the flow diagram for our project. In our project, we are going to encode the data. The encoded data should be the same as the received data. The receiver side, the decoder is implemented. The data bits is 12 bits. The key bits is also 12 bits. The division process is carried out. The division process is carried out based on the XOR gate. The remainder data will be given to the priority encoder to detect the high value on the most significant bit. The number of zeros on the most significant bits is added to the right side of the remainder. The process is carried out again and again. Then the permanent remainder is given. The remainder bits which is added to the data bits. On the whole, the total number of bits will be 24 bits. We have to create the majority gate to detect the majority bit. The majority bit will be 1 or 0 based on the maximum number of 1s and 0s in the data and remainder bits. The data bits and remainder bits along with the majority bits is total 25 bits. It is given to the receiver side. Then we have to split the receiver side, we have to split the last bit of the data and given us the input to the decoder. Then we have to measure the majority bit. Then if the majority bit is equal, then the output will be true. The majority bit, both the majority bits of the center and the receiver side is measured. If the both are equal, then the result then the first step is implemented. Then again the data bits and remainder bit is given as the data bits, then we have to divide it by the key bit. In the whole process, the XOR gate is also implemented. The remainder will be also for the product. The remainder is also the same as the output data. The data should give the 0 values. Finally, we are going to see the output product for our product. The output is implemented in the Xilinx software version 14.2. The Goalie code encoder is our project. We have to click the simulation for the simulation result. The coding will be highlighted. We have to again press the simulate behavioral model. The simulation model is implemented on the icing. For the clock, we have to give the force clock. The leading edge will be 1 and trailing edge will be 0. The period will be 1000 nanoseconds. Then you have to click the apply and OK. Then we have to click the reset button. Now this time we have to give the force constant and the value should be 1. We have to press the run. Then we have to again force constant. Then we have to give the value as 0. Apply and then OK. Then we have to run the time specified on the toolbar. Again press on the run time for the toolbar. The output will be displayed. Then we have to close the iSIM. Thus we have successfully implemented our project.